In this video, we are going to learn about perfect square trinomials and difference of two squares. Now, a perfect square trinomial is a trinomial that is the square of a binomial. So if you have two terms being added or subtracted together, the resulting trinomial from squaring it is a perfect square trinomial. So if ax squared plus bx plus c, a general quadratic expression, is a perfect square trinomial, first and foremost, the outer terms, ax squared, and c, have to be squares of the terms of the binomial. You'll see up here in this definition we have a squared and b squared, which are squares of a and b. And even over here I have a squared and b squared, which are the squares of a and negative b, because when you square negative b, it becomes positive. But then that middle term is always twice the product of the terms of the binomial. So you'll see here 2ab, that's a times b, and then times 2. Now, if this b is negative, that means that these terms are opposite in sign. So here's two examples of perfect square trinomials. One is x squared plus 10x plus 25. You notice the outer terms are perfect squares. One is x squared and one is 5 squared. And those are the terms inside the binomial, x and 5. And if you notice the 10x, that is x times 5, 5x, and then twice that product. That's where that term would come from. So we can factor x squared plus 10x plus 25 into x plus 5 squared. On the right, we'll see one with some bigger values. We'll see 25x squared and 144. 25 and 144 are perfect squares of 5 and 12. And we have x squared, so it'll be 5x for my first term. That's how I get 25x squared. Now this negative 120x, we have a negative here, so these terms need to be opposite in value. That's why we're using negative 12 rather than positive 12. And if I were to do 5 times negative 12, that's negative 60x times it by 2. Twice of that product is negative 120x. So those are two examples of perfect squares trinomials. Now, if you tried to factor these expressions, the way you would do it is you would first see if the outer terms are perfect squares. We'll see here 4x squared and 36 are perfect squares. So I would deduce that maybe this is equal to 2x, because 2 squared is 4x squared is x squared, and 36 would be 6 squared. And to see if we can factor it into this, we're going to check if we multiply 2x times 6, we get 12x. Double of that is 24x, but since I want it to be negative, I'll make that 2x minus 6. So now it's negative 12x times 2, which is negative 24x. So when it is a perfect square trinomial, it's actually a very quick way to factor it. Even over here, let's say that leading term is 64x squared and the last term is 1. Well, it turns out that 1 is a perfect square of 1. So we have 8x and 1. You see here, I often leave off this sign until I know for sure it's positive or negative. But I do know that 8 squared is 64, x squared is x, and 1 squared is 1. Now, 8x times 1 is 8x. Then twice of that is 16x, which is positive. So I'll put a plus sign there. So I'll get a positive 16x. So the factored form is 8x plus 1 squared. So you can see it's relatively simple to factor them as long as you recognize that pattern. And what you're really looking for are those outer two terms, the ax squared and the c, to see if they are squares, perfect squares. If they aren't, then this might not be the method you can take to factor it. Now next we have difference of two squares, which, just as the title says, is two perfect squares and their difference. Now when you factor a difference of two squares, they'll factor into their terms, which into two factors, both of which are no longer squared. So a plus b and a minus b, and whenever you change that sign just in between the two, that's how you make conjugate pairs. So these two pairs are conjugates, just because one's a plus b and one's a minus b. So an example of this on the right, if you have 4x squared minus 9, you also notice there's no middle term either, no x term. it factors into 2x plus 3, which is 2 squared is 4, x squared is x squared, and then 3 squared is 9. And then 2x minus 3, so they're conjugate pairs when they factor. So if you want to see this at play, if you saw x squared minus 4, these are both perfect squares that are being subtracted. So when I go to factor, I'll put x plus 2 and x minus 2 because I have x squared and 4. I'm taking the square root of both of those to get that term, and then I make them conjugates. If I were to use the factoring method, I would be looking for two terms that multiply to negative 4 but add to 0. And the two terms that would do this are negative 2 and 2. Because those add together give me 0, the missing term in my expression for this quadratic. So that's why it factors as such. So even over here, there's no middle term. So again, they're going to have to be opposite in value. The numbers we're looking for in order to factor. So the quick way to do this would be 25, the square root of that is 5. X squared, square root is x. And then 49, its square root is 7. So we'll put 5x plus 7. And its other factor, 5x minus 7. And if I were to use the a times c approach, I would get a number and then find two numbers that multiply to give me that number but add to 0. That would give me these opposite factors when I'm finished. So if I try this again, I have 6x squared minus 81. The square root of 16 is 4x. The square root of 81 is 9. So I have 4x plus 9 and 4x minus 9. It's that simple. And that's how you factor difference of two squares. Now, let me show you another example of a situation that may arise when you're using these factoring techniques. So here I have 4z squared minus 10z plus 25. So I'm already seeing here this isn't difference of squares, but it could possibly be a perfect square trinomial because the outer two terms are positive squares. 4z squared and 25, which if I were to use this technique, I would see that as 2z and 5. But if I were to multiply these together, I would get 10z. I see this is negative, so it's maybe negative minus 5. But I would get negative 10z when I multiply, but since that middle term, bx, has to be twice that product, I can already tell it's not going to be equal to this. Just on that fact alone. If I were to try to use the a times c approach, I can see that a times c is equal to 100. There's no way to get two numbers that multiply to 100, but then add to negative 10. The closest you might be able to get is 20 times 5, but make one of them negative. So maybe 5 and negative 20. But this will add to give us negative 15. So you could try this for a long time, but you'll never find anything that factors this. So I'm going to say it's not factorable. There's not even any common terms throughout the expression. Now, sometimes you may be misled. You'll see here you have 4x squared, but you have 8 at the end. So this is not a perfect square trinomial. But they do all have a common factor. So I could go ahead and factor out that 4 they all have in common. So 4, divide everything by 4. X squared plus 4x plus 2. And then I would get down to this quadratic, and I'm looking for two numbers that would multiply to 2, but add to 4. And that just simply won't happen, because it either has to be 1 and 2, or negative 1 and negative 2. Both of these do not add to 4. So your final answer would just be 4 times x squared plus 4x plus 2. Now, the last example, you may get 81y squared plus 49, which is two perfect squares, but it isn't difference of squares, so we cannot use this pattern. That would actually fall onto a perfect square trinomials pattern of them both being positive. But we can see here that there's no middle term, So there's no way to actually make a perfect squared trinomial situation. So this will not be factorable. And for further proof as that this is not factorable, we could multiply 81 times 49 and try to do the A times C approach. And you'll get 3,969. But again, there's not going to be any two factors that when I add them together, it's going to give me 0 because I have to make a positive number instead of a negative number like you saw earlier. And that's why this situation will not be factorable. This is actually a situation called sum of squares, which will be discussed in a later lesson. And that is perfect squared trinomials and difference of two squares.